Does anyone recognise this film? It's the infamous scene from James Bond Goldfinger, where the evil villain's trying to dispose of Bond by placing him in the path of a high-power laser cutting through metal. But you might also remember that the laser's moving quite slowly, giving Bond time to distract the villain and to escape. In short, the poor performance of the available laser technology led to the failure of the application, and of course, great end-user dissatisfaction. Now, I'm Rob Woodward with the Physics Department, and my research aims to improve the performance of laser sources such as those used for materials processing. Specifically, I'm considering ultra-fast lasers, which produce a series of very short optical pulses of high-power light, rather than a continuous wave with a constant power across time. And these short pulses mean you can deposit energy into materials quicker than they can heat up and thermally damage, so you can process them with a higher quality of finish. And if you can get higher power pulses, you can also process them more efficiently and more quickly. To build an ultrafast laser, you need a device called a saturable absorber. Now, a saturable absorber acts a little bit like an optical shutter or switch, opening and closing very quickly to chop the light up into a series of short bursts or pulses. And the more rapidly that this shutter can open and close, the shorter the pulses that you can get out. Now, saturable absorbers do already exist commercially. They're often based on materials known as semiconductors, which are slower than we might like and only work over a certain range of wavelengths or colours. So my research is considering alternative saturable absorber materials, and specifically a new and a very exciting class of materials known as nanomaterials, which have key length scales on the order of 1 or 2 atomic layers. Graphene is perhaps the best known example of this. So our collaborators in Cambridge have fabricated nanomaterials for us, and we perform measurements here at Imperial that shows they can in fact be ultra-fast saturable absorbers. In fact, they're quicker than any other known material. What's even more exciting is that some of these materials can work at any wavelength. I mean, you can make a single device, and it'll work with numerous different types of laser. And to prove this, throughout my PhD, I've developed a number of sources that can produce pulses as short as hundreds of femtoseconds, less than a millionth of a second. So while work remains to turn these from lab demonstrations into commercial products, there are exciting opportunities of nanomaterials for ultrafast lasers, pushing their impact in industry, opening new applications in science and medicine, and of course, making them an essential tool in the arsenal of any 21st century evil villain. Thank you.